Okay, and we have our final speaker for this session, Romaine Klein from ESPCI.
Thank you very much. So where's the point? Today I will be speaking to you about characterization of automobile material emissions by TD-GC GC-TOFMS, and more specifically car odors. This is work between two laboratories, the ESPCI and the CRNL in Lyon, and also in collaboration with Renault. First of all, I will have to introduce you the subjects and more specifically the problematic of the VOCs, the volatile organic compounds in cars. Thanks to Laura McGregor for introducing the subject. And there are many people already working on pollutant surveillance, and myself, more specifically, I focus on the odors in cars, only odorous compounds, and even more specifically on a material emissions perspective. We will not be looking for anything doing with exhaust emissions or driving. We focus only on the emissions of cars passively. When you work with odors in general, you must have a double approach because there is no link between the chemical structure and the odor of molecule. You cannot guess the odor of molecule only with its structure. And because of this, there is an analytical point of view using most of the time GCMS to get the composition, and on the other side, sensory analysis with an odor panel, people smelling things, to get the odor. The general goal is to find the origin of odors, to anticipate and manage them. This strategy, combining GCMS and an odor panel, sometimes it works very well. Such here, for example, the odor panel detected a very high solvented odor in a material, and the GCMS, in GCMS there was a very intense peak right there, and this peak, it was MMA, methyl methacrylate. Thanks to all this information, they were able to find the problem. It was PMMA that did not polymerize well and thus resulting a bad smell. But the more common chromatogram looks much more like this. So this is a routine analysis of a polypropylene, and all the identified molecules were hydrocarbons, which are little or not odorous. And when the formulation of the material changes, for example, because you use recycled elements to produce them, the chromatogram does not change, but the smell does. So there are molecules that are odorous that we cannot see, either because they are screened by the hydrocarbons, either because they are too diluted. So we need better analytical performances, and for this, GCxGC seems to be the best one. Now I will present you what the method I developed, the GCxGC method I developed to detect as many odorous compounds I could in these material emissions. And first of all, I have to talk to you about the risk of materials that we heat in a microchamber. This produces emissions, and we collected these emissions into some adsorbent tubes. So we collect gaseous emissions, and then we'll bring them to the experimental setup, which is this. We have the thermodesorber on the right to use the thermodesorber tubes adsorbents, heat them, and release the compounds into the GC, which has two ovens. So we can work on the temperature for the second dimension and the TOFMS for the detection. On the right, a TD-100XR by Marquez, and on the left, a Pegasus BT4D by LECO. This is important to notice because it was the first time a Marquez thermodesorber and LECO GCMS were combined. It gave us a few troubles, but now everything is solved. And I've heard this setup has been reproduced elsewhere, so it works. Now that we have the setup, what did I do for GCxGC method development? First of all, the strategy. We are looking for everything, everywhere. We want to detect as many compounds as possible. And so we are doing untargeted, and more specifically, we are focusing on polar molecules. So alkane separation is anything polar must be separated and detected. First of all, we did some preliminary experiments using various car materials. We tested normal, reverse configurations, and we compared the global separation profiles. And with this, we selected three configurations, one normal and two reverse, and we compared them numerically with objective criteria, which were the number and the quality of peaks with the mass spectra similarity. Because after the phase selection, we had this kind of chromatogram. This is a normal phase, normal separation, and even if it did not look like as beautiful as the reverse one, numerically we saw more molecules, so it was more interesting. So non-polar column in first dimension and mid-polar in the second. And if you look at all the peaks, there were around 500 identifiable peaks. Out of them, 200 were potential odorants. After after the phase selection, we tried to improve the method. We trying to make variations of the length and diameter of the second column. Why did we do that? It was because of the pressure of the system, especially for the thermodesorber. So I was first using the column at the top, 100 centimeter and 0.1 diameter, and you can see here that the secondary column has a very high impact on the global pressure of the system. And on the documentation, we were not supposed to go above 60 psi for the thermodesorber, so it was respected. But experimentally, we have seen that it was better for the thermodesorber to be below 40 psi at rest. It still works, but you have to increase the maintenance, and that was problematic. Here, it seems that the best column is the short and large one, 50 centimeters, 0.18 diameter. But if we improve the TD durability, don't we lose separation? That would be problematic. So we compared these four column configurations on several materials. So here a trunk mat, a seat foam, and a textile. And we compared how many peaks were able to see depending on this. And here, if we compare the column on the left, which were the long and thin one we were using at first, the results are not that different from the 50 centimeters and 0.18 diameter. So even if we seem to lose a little separation, the TD durability is strongly increased, and this is truly beneficial for the system. So now we have concluded our GCxGC method development while managing TD constraints. So short and large 2D column to reduce the pressure, and we also use the 2D oven temperature to reduce separation time. Now it's time to focus on a few selected materials that we will study deeply. Here are the 8 materials I studied. They are all around the cars, the inside of the car, and we will more specifically research odorous molecules. This is what we are looking for. First of all, the raw chromatogram. Because I'm looking for very diluted polar molecules, which you can see above the baseline of alkanes. Here is the baseline of alkanes, and above all the polar molecules. As I'm looking for diluted molecules, I like contrast on my chromatogram. This is why you can see some trails on the second dimension. After automated peak finding, we have about 800 peaks, and after manual peak validation, which takes about 3 days, we have 150 or 144 potential odorants, and compared to the literature, we had 113 confirmed odorants. This is a lot. It won't be possible to explain the whole odor of one sample with 1, 2, 3 molecules. We'll have to take into account 100 molecules. With the four materials I studied, I established a list between 75 and 150 odorous molecules per material, and this is the molecules we'll use to try to explain globally the odor of all these materials. Now we have the chemical composition of emissions of these materials. What is their smell? And how can we compare the smell to the chemical emissions? This is what I did in Lyon, where I did sensory experiments. First, I use fragments of materials. I put them in a vial, and hitting the vial, I get these emissions, and then I present it to participants by opening the vial. We measure the respiration with this pressure capture, which you can see is linked with a cannula to the nose of the participants. And we also ask them to rate several criteria: hedonicity, intensity, description. Today, I will only focus on description to try to link it to chemistry. For every vial, participants were asked to say whether or not, on a binary criteria, whether or not all these 14 descriptors were present or not. These descriptors try to be objective and not subjective. We try to remove any influence of context. They did not know these materials came from cars. And after that, we did a first campaign where we had 7 materials and some reference to open the context of others, and we got 69 values per material. We reproduced this experiment on a second campaign with fewer materials and more trials. And in the end, every material got 1 rating per descriptor per campaign, and it was 1 value between 0 and 1, the mean of all these binary ratings. And now I will only focus on these 4 materials: the ABS, the PP1 polypropylene, the first Nicor, and the POF. Now, how do we link chemical and sensory data? We have on one side between 75 and 150 molecules we have detected in these emissions, odorous molecules, and 14 descriptors. This is too large to be manipulated easily, so we'll use principal component analysis, PCA, to differentiate these emissions. On the chemical side, we had 2 duplicates per materials, and here we can see that the duplicates, despite working on thermodesorption and having very large variations between the 2 duplicates when we checked every molecule individually, they were very close on PCA, so this is a good point. The 2 duplicates for every materials were chemically close in comparison to the others. When we look at the molecule contributions individually to this principal component analysis, we have this 191 molecules. That's not easy to read, and even less when we add the sensory descriptors in blue. So 191 molecules in red and 14 times 2, 28 descriptors in blue for the 2 campaigns. And now we put an hypothesis, which is that maybe you could try to explain the presence of one descriptor in particular and the presence of some molecules and link them depending on their distance on this graph. To do this, we'll extract the 3 first coordinates on this PCA and weight them by the PC. So every coordinate on the first dimension multiplied by 42, second dimension by 29, and so on. And in the end, when we try to see the distance between all these molecules and descriptors globally, we got this. So on this dendrogram, we group progressively all these by distance, and we can see 11 descriptors. For these 11 descriptors that are highlighted here, they were used to describe chemically similar stimulations. They were close. They are close on this dendrogram, close from one another. So on the two campaigns, these descriptors were used to describe chemically similar stimulations. So we can suppose that the molecules close to them are linked to the use of this description. If we try an example to know whether or not it works, we can look here near the gasoline in black. Near the gasoline descriptor, we have several molecules, and for some of them, we could expect them to explain the gasoline smell, such as toluene or styrene. But for some others, such as butanol, benzaldehyde, and propanoic acid, you may not expect them to be gasoline. It could be something more acidic, more solvented. Here they are. And is it just coincidental, or are there interactions? If you mix two molecules, you do not have just a sum. They may interact in your nose and produce a completely different smell. So when you have 200 molecules, it doesn't work as you expect. So maybe if we mix all of parts of these molecules, we may have a gasoline smell. We'll need to check this experimentally, but the interesting thing in this study is that we considered the global contribution of these molecules to the smell. We didn't try to explain the smell with 100 molecules individually, but globally, and now we're trying to link the perception to these molecules. And of course, we'll need further experimental assessments to say whether or not a mix of these molecules smells like this or not. I thank you for your attention, and if you have questions.